In this video, we're going to tackle question 1 from the Triangle of Forces tutorial sheet. In this question, we've been given a block that's been acted upon by two forces. One is a horizontal force of 60 newtons, and the other is acting upwards at an angle of 60 degrees from the horizontal, and that's of size 30 newtons. In the question, we're asked, what third force would we have to add to this block in order to keep it at rest? The third force might be some combination of weight and friction, but we're not asked to comment on that. We're simply asked to determine what the third force must be for this block not to be moving. And so in order to tackle this problem, we're going to use a graphical method. We're going to draw a scale diagram of the forces. And what will happen is once we've drawn in the two forces we're given to scale, they'll form two sides of a triangle. And the third side of that triangle will give us the size and direction of the missing force we're looking for. So that's how we're going to tackle this. Let's set it out one stage at a time. Because it's a scale diagram, we have to establish what our scale is going to be. Now, it's slightly harder to see on the whiteboard screen, but I use an interval of this length to represent what I would call on a real ruler on a real page 1 centimetre. This line here, we're going to call 1 centimetre on my ruler to give you an idea of what you'd have on the page. And what I think may be a sensible scale for a question like this is to say 1 centimetre will be equal to 5 newtons. Now, you can make your scale different to that, probably a bigger scale rather than a smaller scale. You could make 1 centimetre equal to 3 newtons and probably still fit that on an A4 piece of paper. It's about drawing your diagram small enough so it'll fit in your page, but big enough so you can still accurately measure any additional lines that you draw and keep it nice and accurate. So having established our scale, we're going to draw in each of these vectors. And as we do in the graphical method, we'll draw the vectors joined together, so they won't all be coming out a central point like they are on the block at the moment. We'll draw one vector, and then from the end of that vector, we'll draw the next one. So let's start off with the easier of the two. Let's draw in the 60 kilonewton vector, the 60 newton vector. Now we've said that 1 centimetre on our ruler is going to represent 5 newtons. So a 60 newton force has to therefore be 12 centimetres long. So I'm going to draw an interval of 12 centimetres to represent that horizontal vector as accurate as I can. This is 12 intervals of my ruler are 12 centimetres. The direction is really important here, so we'll indicate this with a little arrowhead at the end of it, and I'll just mark it that's a 60 newton vector as well, just to keep us right. We now want to draw a second vector, this time representing the 30 newton vector. That's the second one from our diagram, and that has to be an angle of 60 degrees above the horizontal line. It's got to start, it's got to start from this point here. It starts where we finished with the previous vector. So I'll just mark out a little dotted line because it's easy for me to measure. The ruler automatically measures angles for me, but if you're doing this in your own piece of paper, you might extend your line with a wee dotted line here, and then you'd use your protractor and you'd measure an angle of 60 degrees up from this line. So I'm fortunate on the computer, my ruler tells me what angle it's at. But what you would do is you get your protractor out and you'd measure an angle between that dotted line and the line of the ruler I've lined up here of 60 degrees, and you'd mark that out, and then you would draw up a line. So in your protractor, you'd make a wee dot and then you'd draw through it here. So, and this line needs to be 30 newtons. So in this case, for our scale, 1 centimetre being 5 newtons, this line is 6 centimetres long. So it takes us up to here. And again, I'll indicate the direction with an arrow. With the 30 Newton vector, I'm just keeping my angles marked in here, 60 degrees, so that I can see that, yes, I have 60 degrees here, I have 60 degrees here. I am keeping these lines. It's like taking the individual lines from the diagram and just pulling them apart and joining them end to end. So we know that the block is going to be at rest, which means we have to have a triangle of vectors that takes us back to the start. That means a final force going from the end of our 30 Newton vector back to the start. Now, I should say it wouldn't have mattered which order. If we'd done the 30 Newton vector first and then the 60 Newton vector, the line we end up drawing would still have the same size and the same direction. And you can try that to convince yourself if you want to, when you've done it that way already. So get the ruler out again, and this time I'm going to draw a line joining up the end of that 30 Newton vector and the start of our 60 Newton vector. I think this looks about right. This is perhaps the best that I can manage here. And I'll use red for this just to show it's the new thing we're finding. So the first thing you do is you draw in your line like this. Make sure to include the direction of it as well. That's important. And what we're going to do is we're going to measure this line and use our scale to find out how big it is in terms of newtons. So I'm going to start off there and count along. So I'm going to 2, 4, 6, 8, 10, 12, 14, 15, or maybe it's about 15.8 centimetres. Now I'm having to be very approximate here. You'd be much more accurate on a real ruler and paper. But say this is 15.8 centimetres, which I think is roughly what it is. Well, 15.8 centimetres is equal to 15.8 times 5, which is 79 newtons. Now, this feels about right. We know the line looks longer than the 60 Newton line, so that seems pretty accurate. Again, what you'll also do is you'll measure an angle for this line, and a sensible thing to do is to go to the start of the line and again put out a little dotted line here. And depending which way it's pointing, up or down, measure up or down from the horizontal line. So this is pointing down from the horizontal, so you'd get your protractor and you'd measure this angle here. This is what we mean by the direction of the force. But I can fortunately measure down with my ruler, and it tells me the line runs down at 19 degrees. So I can mark that in here. So I might say something like, for my final answer, and I can just type this in to save my handwriting. Additional force has, well, we can use the word magnitude, that's a word for size. Magnitude 79 newtons and direction 19 degrees below the negative direction of horizontal, because it's acting to the left. That's the negative direction. And there's different ways to give that. The most important thing is you make it clear. So there's not one way to say this is the direction. You could use a system of bearings. You could say, you could have drawn in something like this just to make it clear to me that you meant 19. There's also arrow to show the vector there and say, oh, it's 79 newtons. As long as it's clear, you get the marks. And to be honest, as long as you mark it in the diagram, as long as it's in here somewhere what the direction is, you can be given full marks for a question like this. And that's how we go about solving question 1 from the tutorial sheet.